name is Philippos Kozagos, and here is my Lab4 presentation about oscillations. The purpose was to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. Introduction: our goal was to compare the predicted motion and the observed motion of a mass attached to a string. Also to plot the energy changes that we have computed in the model. To plot the change in kinetic energy, the change in gravitational potential energy, the change in spring potential energy, and the change in total energy. Some of the results, findings: the predicted motion and the observed motion are similar in the x-axis as well in the y-axis, and the change in the total energy is 0. Main concepts: Newton's second law, the net force of an object equals to the change in momentum over the change in time, and some of the formulas that connect velocity and the net force are the following, as you can see here: 1, 2, and 3. Also, the energy principle: the change in energy of the system equals to work done on the system by the surroundings plus the change of thermal energy between the system and the surroundings. Important note: when we are dealing with energies, and we must define our system and also our surroundings. Some of the equations of the energies that we will use in this lab experiment are the following: the gravitational kinetic energy, the spring potential energy, and the gravitational potential energy on Earth. Define our system, which is Earth spring mass, surroundings nothing, since we consider that the system has all the elements that do work on the mass. As a result, work of the surroundings equal to 0, Q equals to 0, so delta E system equals to 0. 3-point diagram: static equilibrium position, F net equals to 0, F net equals to Fg plus Fs. Delta E system equals to delta K plus delta U G plus delta US, and we just plug the equations there. Tracker model analysis: this is the video of my tracker. Some details: the mass, 0.402 observations, the initial position, the initial velocity, and the time of the last observations are presented in this slide. Computational model: initial conditions derived from tracker model, ball mass, position, velocity, and delta T. Some other important things to mention: the gravitational constant 9.8, the spring constant, and L0. We can find K and L0 by these two equations here that you can see. Model code: distance from relaxed states to find L, L hat, and S. Energies: here are the energies applied, equations of the energies applied. Net force, velocity update, position update equations, you can see them here, pretty easy and well defined. The while loop: while t is less than 8.927, which was the last moment that I recorded my motion. And here, compare track analysis to computational model, you can see the code here. The results: the results in graph, the change in energy versus time, the time versus exposition versus time, the y position versus time. Important things to consider: change in energy versus time in graph. The change in the spring and potential energy increases, more positive; the change in the gravitational potential energy decreases, more negative, and vice versa. The position versus time graphs: the model can accurately predict the exposition of the exposition versus time graph. The model does not predict as accurate the y position of the y position versus time graph. Potential sources of error: might not accurately track the center of mass of the object during the tracking analysis, not taking into consideration other forces such as the drag force, and not taking into consideration other energies such as thermal energy, rotational kinetic energy. What does it mean? Satisfaction: we have satisfaction of the energy principle. Looking at the change in energy versus time graph, we can observe that the sum of all of the energies equals to 0. This is the orange here, the orange line here. The sum shows that nothing from the surroundings does work on the system, which verifies our initial definition of the system in this lab experiment. Oscillation periods: the time period between two crests is the oscillation period. We can calculate the average period of oscillation by taking the sum of two periods divided by 2. Here are my period of oscillation for x, period of oscillation for y position, the difference between them. Impact of this difference: can be caused by incorrect tracking of the center of mass of the object, also by drag forces acting on the object, and this can influence the calculation of the spring constant K, which K is dependent on the oscillation periods equation. So we will spring force and spring potential energy will get affected. Thank you so much for your time and for your consideration.